So here are some sample questions from the IB question bank for topic 11, specifically for SL students. And I'm hoping after you've gone through this, you'll be able to recognize ways of simplifying your road to the answer through elimination processes, or even looking for specific parts of the spectra of graphs, etc., to help guide you directly to the questions. So the first question here says, what combination is the most effective for reducing random and systematic errors? So the key here is to recognize what makes a random error and what makes a systematic error. Remember, random error are things that are out of your control. There could be the setup of an equipment, so the change in the temperature, the fluctuation, etc. Systematic errors are anything to deal with human errors, so things that you've done that are going to affect the results. So when we talk about random errors, the best way to improve a random error is to repeat a trial. But this doesn't work for a systematic error, because if you've not set up the experiment properly, no matter how many times you repeat it, you're still going to get the same error. So this eliminates this part here, because these are both repeat trials. The only option that you will have then is C, because this is what says about the random error, which is repeating trial. And for the systematic error, I know that if I recalibrate the equipment, that means I am dealing with the error that I originally had. That if I didn't calibrate an equipment, that is a human error, because I didn't start it off the proper way. So this is the only logical answer there, and you can see that I got the answer straight away by focusing on one of the errors rather than focusing on two at the same time. So if we go to the mark scheme, you'll see that the answer is C. The next question is saying, what information about 2-hydroxybutanoic acid can be inferred through the mass spectrometry, MS, infrared spectroscopy, IR, and proton nuclear magnetic resonance, proton NMR. Now, some students might read this and think that's a lot of words, but this is basically the abbreviation for here, and this is the abbreviation for here, and the proton NMR is the abbreviation for the proton nuclear magnetic resonance. So they're telling me that I have a 2-hydroxybutanoic acid, and they're asking you for each of this, what information would I get out of it? So if I'm looking at the mass spec, for example, I would know that the last value that I have in the mass spec is going to be the molar mass of the molecule. Okay, so I can focus on the mass spec. I can look at the IR, since I know that it's a carboxylic acid because it ends in oic acid. Then it should have two peaks, the carbonyl group, and it should have the OH group. And from the proton NMR, I'll also see some information about the proton environment. Okay, so it's enough to understand what each of these do. So the important thing to recognize here is that the mass spec doesn't tell me anything about the information about the hydrogen environment. That can only be found from the proton NMR. The IR can only tell me the type of bonds that are absorbed when the molecule is vibrating. And then MS basically tells me the fragmentation of the ions. So if we look at the first column here, which is the MS, we can see that there's two parts of the information. I have 104 grams per mole. And as you remember from the mass spec, the last peak that I see is that of the molar mass of the molecule. And another thing that it shows here in this column is that the compound contains carboxyl and hydroxyl groups. I can easily eliminate this from here, or I can look at it from another way in terms of the IR and the proton NMR. Okay, so if I look at the IR is not going to give me the molar mass of the molecule, and the proton NMR is also not going to give me the molar mass of the molecule. So I can eliminate these two options here automatically. That leaves me with option A or option B. So then I'll look to the next one, and then I try to recognize what does the IR give me and what does the proton NMR give me. So if I look at option A, the compound contains carboxyl and hydroxyl group. Yes, I can get this from the IR because it's telling me the bond vibration at a specific region. I know that I will, for example, have a carbonyl group and I will have an OH group at specific peaks. The proton NMR, the hydroxyl group is on the second rather than the fourth carbon. Yes, I can get this information because it's all about the proton environment. So option A is the likely winner here. And I can prove this to say that I cannot have a proton environment in the IR. So this is not an option. And I can see what the compound, that it contains carboxyl and hydroxyl group from the proton NMR, but I can't see it in the IR. So the only logical answer here is A. All right, next question is about the mass spec. Which compound produces this mass spec here? So this is important to go back to the mass spec details that you have. So if I look here, okay, I can recognize a few features that I'd need for identifying the molecule. So let's look at the molecules that I have. So these are the molecules that I have, okay? So then I'll look at the mass spec and try to figure out what are the major peaks that I see that are going to give me this information. Well, first of all, I see this peak here at 45. And if I go back to my data booklet, I can see that at 45 I have the carboxylic acid, the COOH group there. What I also see is another peak here at 15, and that tells me I also have a methyl group there. So if I look at my molecule, the only option that I can see that's got the carboxylic acid, okay, which is that big peak here at 45, is option C. You see that it's missing from these molecules and it's only present with C. So I don't need to do any work here. I just need to identify the major peaks that I see. I don't even need to calculate the molar mass of the molecule. I just need to be able to figure out what are the major peaks that I see that give rise to this molecule. And always, always, always use the data booklet. So you can see that the answer there is option C. Okay, next question here is I need to find the index of hydrogen deficiency, which is IHD, of this molecule here. Okay, so the best way to answer this question is to write down the molecular formula. Okay, so the first thing that I need to do is to calculate how many carbon atoms I have. So I have 6 in this group here. So if I write C, I've got 6, 7, 8. Okay, so this is for the carbon. And then I count the hydrogen. You always start off with carbon, hydrogen, and then you do things in the alphabetical order, O, N, etc. So here I have the carbon and then the hydrogen. I would count 1. Please don't forget these hydrogens here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I have 2 oxygen atoms, so that's O2. And then I have 1 nitrogen atom. Now, if you remember from the IHD, the formula that I need to use is that of the alkane, so it's CN, H2N, plus 2. Also, a reminder that anytime I see an oxygen, the oxygen is not going to affect the molecule. But if I see a nitrogen, what I need to do is add 1 to the carbon and add 1 to the hydrogen. So that would mean that now I have C, 8 plus 1 is 9. And then the hydrogen is 9 plus 1 is 10. Remember that the nitrogen adds 1 to the carbon and 1 to the hydrogen, and the oxygen doesn't have any effect. So now I need to find the IHD. Okay, using this formula here. So this is 2N, and N in this case is 9. So 2 times 9. Okay, plus 2. So this is the alkane formula that I have. Minus 10, because that's how many hydrogens I have here. And I divide all of this by 2. So 2 times 9 is 18, plus 2 is 20, minus 10 is 10. And then 10 divided by 2 gives me 5. And that's how basically you calculate the IHD. So the answer should be C. Okay, this next question asks me how many signals are observed in the proton NMR of this compound here. This is a very easy question because if you look at this molecule, you can clearly see that it's symmetrical. Any way that I flip it, the left and the right look exactly the same. So I should see only 1 signal there. So the correct answer is A. Next question, what is the uncertainty in centimeters cube of this measurement here? Okay, so this is a burette. Okay, you can see that the measurements are by 1. Okay, so 1, 2, 3, 4, 5. So this would have been 1, 5. I've got 2 decimal places there. So then the option is plus or minus 0.15. Remember, because you are going to 0.05 of the instrument that you're using. So the answer is C. Okay, Next question is a very typical question. It's asking me for the slope of the graph. The easiest way you can do that is to try to find an x coordinate and an x-intercept or a y-intercept. So I can clearly see that here I have a y-intercept, so I would take this point, and remember with the slope, to find the slope, I need the change in y over the change in x. So in order to do that, I need to take 2 points in order to carry out this calculation. So this point here is 0 for x. Remember, we always start with x. So this is going to be 0, comma, 0.2. Please be very careful with the numbers that they've given you, because if you make mistakes in writing them down, that might give you the wrong option. Okay, and then the next point I would take as the last point here. So then x in this case is 60. And y is 0.05. You can take any points that you want, but I find these the easiest. So now I need to subtract these values together. It doesn't matter which way that you want to go. The final initial, it'll still give you the same information. So let's do the second point minus the first point. So we've got 0.05 minus 0.2. Divided by 60 minus 0. So when I do the calculations for this, I should get 0.05 minus 0.2 divided by 60. So this gives me minus 0.0025. And the unit is going to be mole per decimeters cube per second. So then the answer to that is going to be A. Be very careful with the units. As you can see here, they've given you 2 values, and each of them is going to be differing by the unit that you have. You have a mole per decimeter cube, which is your y-axis, divided by the time, which is in seconds. So this is going to be reciprocal seconds. So then the answer is A. I'm going to skip this question and this question because we've already done something similar. And I'm going to go to this question here. Okay, so to calculate this, I need to find Q. And so Q is going to be MC delta T. So when I do this calculation, I should get about 844.36 joules. Okay, so then I have to look at these here, which are my uncertainties. You can see that the temperature is the one that's going to give the most uncertainty. The 0.2 isn't going to make much of a difference, so I'm just going to be taking the 1. And to find the uncertainty, all I need to do is divide the uncertainty by the measurement that you have, which is 844.36. Okay, and then multiply that by 100, and then your answer should be C. 11. Alright, which region of the electromagnetic spectrum is used to identify hydrogen environments in a molecule? Anytime you're asked for a hydrogen environment in a molecule, you're asked for the proton NMR, and the proton NMR always is in the radio waves. So the answer should be D. What can be deduced from the IR spectrum of a compound? I cannot tell the number of hydrogen atoms. Okay, this is only going to be from my proton NMR. I can't tell the number of hydrogen environments. Again, this is going to be from my proton NMR. It doesn't tell me the molar mass. The only thing it can tell me is the bond present, which is option C. Okay, which is correct for the spectra of organic compounds? The mass spectroscopy provides information about bond vibrations. That's going to be incorrect because this is what the IR does. Proton NMR spectroscopy provides the values of carbon-hydrogen bond lengths. That is incorrect. Inferred spectroscopy provides the number of hydrogen atoms. That is incorrect. Mass spectroscopy provides information about the structure. This is the only logical answer that is there. Moving on to the next few questions. What is the ratio of areas under each signal in the proton NMR of 2-methylbutane? So the only way to answer this question is to actually draw the molecule that you have. And remember, when we talk about the areas under each signal, is basically how many protons do you have under each integral. Remember, this is the integral, okay? So this tells me how many hydrogens that you have in the NMR spectrum. So I have a molecule that is 2-methylbutane. First of all, I draw my longest chain, which is a butane. So this means that I have 4 carbons. And I know that at position 2, I have a methyl, so I draw my methyl. And then the rest of the molecule is going to be made up of my hydrogens around the carbon. And I'm taking time to draw this because once I draw it, it's going to make it really easy for you to understand how to answer this kind of question with ease and to eliminate 3 at the same time. Okay, so now that I've drawn this, I'm going to count how many hydrogen environments that are the same. So you can see that here I have a carbon with 3 hydrogens and a carbon with 3 hydrogens that are almost the same. Okay, so we can say that they're in the same chemical environment. And if you count the total number of hydrogens here, you can see that they are 6. Then the second environment is the CH3 here on the second carbon. This is a hydrogen by itself, which is my third, okay? And then I have a CH2 here. Okay, so I have 2 hydrogens here, 1 hydrogen here, and then 3 hydrogens here, okay, for 4 environments. So I can automatically eliminate D. I don't have that many there. And I can remove B. I'm left with A and C can also be eliminated because this tells me that I only have 3 environments, but I actually have 4. And you can see that these are my 6 here. Okay, this is my 1 here, these are my 2 here, and this is my 3 here. Okay, so again, to solve this kind of question, first draw out your molecule, start with your longest chain, and then put in your side chains, and then locate how many kind of hydrogen environments that you have. If you see 2 that are going to be the same, then you label them as 1 environment, and you circle all the other environments. So then your answer should be reflective of how many environments that you've chosen. So then the only answer there is A, as you can see also from the mark scheme there. Which feature of a molecule does infrared spectroscopy detect or spectrometry detect? It does not detect the molar mass. It does tell me about the bonds present. It doesn't tell me anything about the total number of protons or their environments. That's for the proton NMR. So then the only logical answer there is B. How are the uncertainties of 2 quantities combined when the qualities are multiplied together? So this one is very easy. The only answer there is going to be D because you always add the uncertainties at the end. The rate of reaction is studied at different temperatures. What is the best way to plot the data? Okay, remember that when we talk about the x-axis and the y-axis, we have to remember that your y-axis is going to be your dependent variable and the x-axis is going to be your independent variable. So then the answer for this is going to be C, because the type of variable on the x-axis is always going to be your independent, and because you're measuring temperature, this is going to be on the because you're changing the temperature, then this is going to be my independent variable, which is going to have an effect on your dependent variable, which is your y-axis, which is basically what you're measuring. Finally, this last question here, what information is provided by proton NMR, mass spec, and IR for organic compounds? The proton NMR, you can tell the chemical environments of the protons. The MS is the fragmentation pattern, and the IR, the types of the functional groups. So this answer is very easy because it's D, because it gives you all this information about the organic molecule. And I hope this was helpful.